Hi there, my name's Vanita. I'm a tutor here at WhizSmart, and today we're going to be doing a little bit of chemistry. I'm going to be talking to you about balancing chemical equations. So let me get started by sharing my screen. Here we go. Let me present this. Perfect. Yep, so my name is Vanita, and we'll be talking about balancing chemical equations, just as this says. Perfect. So this is a pretty simple one to get started. So what do we have here? We have something that looks like carbon, oxygen, and that makes CO, or carbon monoxide, right? So the thing about this is I see that we have one carbon here, and I see that since we have this little 2 here, we have 2 oxygens. Then over here, I see one carbon, and I see one oxygen, right? So the thing is, if we have 2 of these oxygens here, then where does that other oxygen go once we go here, right? Where does that oxygen go? So the thing is, we need to do something called balancing to make sure everything on the left side is equal to everything on the right side, or everything on the reactant side. Let me spell that out for you. Is equal to the products, okay? Don't mind my handwriting. I'm writing with a trackpad or a mouse pad, so it's a little bit difficult to write. It might look a little bit sloppy, but hopefully we can get the message across. So our reactants and our products have to be equal number of atoms pretty much of each element. So we have one carbon here, we have one oxygen here, or we have 2 oxygens here, my bad. Then we have one carbon and one oxygen, right? So what are we gonna do? Let me erase some of this writing and let's get started. So what we're gonna do is we're gonna say, all right, we have 2 oxygens. So that means we can't really get smaller than that because we can't break up the oxygen because it has this 2 as a subscript, which means that these guys are bonded together, right? So this exists as one molecule. So we have 2 of these oxygens. So what are we going to do? We're going to write a 2 right here. We're going to actually just double this whole. So we're going to take these carbon monoxide molecules and we're going to have 2 of them now. Okay? So we're going to have 2 of those, which gives us 2 oxygens and 2 carbons. But then you might ask, all right, so we have 2 oxygens here, right? And we have 2 carbons here and 2 oxygens, but then we only have 1 carbon here. So what are we going to do? Pretty simple. We're going to also put a 2 here, right? So that means we have 2 carbons, 2 oxygens, 2 carbons, 2 oxygens, and we're fully balanced, completely balanced, and it looks great, right? So that means our final equation would be 2C plus just one O2, right? Because that O already has 2 with it, goes to, and we usually write an arrow for this, 2CO. All right, so that was a pretty basic one. Let me clear this board and let's try a little bit of a harder one, okay? So the main reason that we want to balance these equations is because if you have excess on this side, then not all of it is going to react, right? And if you have excess on this side, well, then you made extra products somehow without enough reactants, right? And we don't want that. So we want everything to be exactly perfectly equal on both sides of the arrow. And the arrow is kind of like an equal sign. It just shows that everything on this left side becomes everything on this right side. So that's kind of like an equal sign. It has to be the exact same. So if I clear that, let's get started. So what I see here is we have one Fe, or iron, on the reactant side. We have one on the product side. And I see 2 of these Cls, right? These chlorine ones. And then I see 3 over here. So I see the Fe's are balanced, right? But the Cls are not, because we only have 2 here and we have 3 over here. So what are we going to do about that? Well, let's see. If we have 3 here and 2 here, I can't just I can't double this 2, right? If I make a 2 here, then I have 4 because I multiply this 2, by this coefficient. This is called a coefficient. And then we get 4, and that doesn't really work, right? Because we still have three CLs here, and you can't really add, you have to multiply. So that doesn't work. So let's erase that, and let's figure something else out. So let's see, if I doubled this one here, right? If I made a 2 here, I would multiply by this 3 CLs, right? This 3 right here. And what would I get? I would get 6, right? And then I take a look. Oops, I didn't erase that fully. There we go. And then I take a look and I say, all right, well, 2 multiplied by, let's say, 3 would also make 6 CLs, right? And guess what? That works perfectly. So then once we do that, our CLs are perfect. We're good to go. So we can put a little check mark there. But then if we look at this iron, this Fe, since we multiplied this by 2, we now have 2 Fe's, right? But we still only have 1 here. So what are we going to do? We're going to put a 2 right here, right? Easy peasy. And so we get that. And so then now we can scribble that one out. We're going to put a 2 there because when we have 2 Fe's, we have our 6 CLs, we have our 2 Fe's here, and our 6 CLs. A good way that I like to use, just to double check my work, is I like to figure out everything that we have in this equation. We have Fe, we have Cl2, or just Cl. We have an Fe and a Cl3, right? So what I see is an Fe and a Cl. Oops. A Cl, right? So I'm going to put these little dashes here. And this side is going to be for our reactants, right? I'm going to put an R there. And this side is going to be our products. So I'm going to put a P there, okay? And what I'm going to do is I'm going to, pretty much these numbers I wrote up top, I'm going to make it a little bit more organized. So I'm going to say, all right, on this side of the arrow, on the left side, I have 2 Fe's. So I'm going to put that there. And then on the right side of the arrow, on this side, I also have 2 Fe's, right? So I'm going to put that there. I'm going to put a 2 and another 2. So that shows we have 2 Fe's on the left, 2 Fe's on the right, 2 Fe's on the reactants, 2 Fe's on the products, right? Left and right, reactants, products, same thing. And then we have 3 here times this 2 right here. So 3 times 2, that gives us what? That gives us 6. So we have 6 CLs here. Oops, let me put that a little bit lower. 6 CLs here, and then we have 2. This 2 applies to everything in this molecule. So 2 times that 3 that's boxed is also what? 6, right? So we can put a 6 right here. And look at that. This 2 is equal to that 2. And the 6 on the chlorine is equal to that 6. So everything is perfectly balanced. We have a 2, a 3, and a 2. So that works just fine. So let me clear this board and let's try next one. So our next one, we still have that iron, we still have that Fe, but now we have oxygen, right? So let's see what we're getting. Let me change my color. All right, so I see 1 iron, 2 oxygen. It's that O2 that we saw before. And then we have 2 irons and 3 oxygens, right? So that 2 and the 3 are similar but not the same, and that 1 and the 2 for the iron are also not the same. So let's see, what are we going to do? I like to usually tackle the biggest molecule I can see, because if I figure that one out, then everything kind of flows. So let's try that. So we want something that has a 3 and a 2 in it, right? And a number that I really like to use is 6, because you can always get a 2, it's a 2 times 3, right? Or it's also a 3 times 2. So for example, we have this O2 which has 2, so we need to multiply that by 3, right? And we have this O3, we need to multiply that by 2 to get a 6. So let's try that. Let's put 2 here. Okay? So we put 2 there, so that gives us 2 times this guy right here is equal to 6. And then let's take a look. Why don't we do this oxygen right here? So we have a 2 here. Multiply that by that 3 to give us a 6 again. So those check out, right? The oxygens are the same on both sides. And then we have this 2 right here. So let's multiply it by this 2 that I'm boxing right here on the iron. And let's see, we have 2 times 2, right? Which is equal to what? 4. Good. Okay, that was a sloppy 4. Let me try that again. There we go. So 2 times 2 is equal to 4, and if we only have 1 Fe, 1 iron, what are we going to do? We're going to multiply that by 4, right? So let's take a look. Let's use pink for this. So I've got 4 irons. Actually, no, let's write it down right here. So we have Fe, we have O, right? And then if I erase my math here with the 6s and the 3s and the 2s, what do we get? So we're going to draw our lines, and this is just like what I said before. On the left side is equal to the reactants, and the right side is equal to the products. So on the left side, we have 4 Fe molecules, 4 iron molecules, right? We have that right here. On the right side, we have this 2 times 2, which is equal to 4, basic multiplication. And then, oops, I made a mistake. This right here should not be a 6, right? That's our total, but we should put a 3 there, because if we take that 3 multiplied by 2, then that gives us 6. So we end up with 6 total, but since we already have this 2 right here, we want to put a 3 down. So we can take 3 multiplied by 2, 3 times 2 is equal to 6. So we have 6 on the left side, and then what do we have? We have a 3 times a 2 is also equal to 6. And look at that, we got the same thing on both sides. So we're good to go, we're perfectly balanced. We won't have, I'll erase that 6 right here, oops, erase that 6. So we just have this 3 instead, right? So we won't have any excess reactants or products. We'll have the exact amount that we need to conduct this chemical reaction. And so pretty much it means whatever units you have, we like to use a special unit called moles, which you'll learn about later. Whatever unit that we have, we'll need 4 of these. For iron, we'll need 3 of these O2s, so make sure it's O2, and that'll give you 2 units of iron oxide, or Fe2O3. All right, let me clear this board, and let's try another one. Alrighty. So I see 1, 2, 3, 4 molecules. Don't get scared by this because there's 4 now instead of the 3 that we've been seeing before. That just means that there's 2 reactants and it'll give you 2 products. Okay? So let me erase these guys so we have space to write so it doesn't get too crowded. So pretty much what this means is just because we have another product, it means that our 2 reactants, they didn't squish together and form just one product, but it means they form 2 different products. So let's see what we want to start with. I see first this Fe right here and this Fe2, right? Let's start with that. So this has 2 irons to our 1. So as we've learned, what do we want to do? We want to double this guy right here so that we have 2 of these, right? So let's leave that there. We have 2, we'll call this a 1 right now. And let's move on to this guy right here. So I see something in parentheses multiplied by a 3 as a subscript. So what this means is that this 3 right here applies to every single thing in the parentheses, every single element or molecule in the parentheses. So that means technically we would have 3 S's and 12 O's, right? Oops, 12 O's. But the cool thing is I see the same kind of cluster right on this side, on the reactant side, which means we don't even have to separate these, right? We don't have to do a lot of tricky math because we have these 12 O's, which is kind of a lot. what we can do is we can say, hey, let's look at this as one unit, okay? So we'll look at this as one unit here and one unit here. So we know we have 3, right? We have this 3. So we have 3 of these units. So what are we going to do? We're going to put a 3 here. We're going to put a 3 there to make 3 of these SO4 units, okay? Let me erase that. Let me erase some of this. Make it a little bit less crowded. There we go. So that's exactly what we did. We took this as a unit, right? And we took this as a unit. This unit was multiplied by 3 because we have that 3 as a little subscript here. So what we can do is we can write the 3 as a coefficient. And one little warning is, let's say we had this FE over here, right? We have this FE and we wanted 2 of them, right? Why do we have to write it with a 2 here? And why can't we write it with a 2 down here, right? Because we had that 2 over here. Why can't we do this? Well, that's because if you write this 2 as a subscript, that means you're taking 2 Fe molecules, right? You're going to add them together. You're going to kind of squish them together, right? And you're going to make them bond to each other to make its own molecule. And the thing is, we can't do that on our own, right? Because we're just adding different things. We're adding some powders, maybe some liquids, depending on what state these different molecules are in. So what we can't do is we can't take, we can't say, all right, let's take these 2 Fe's, squish them together so that they bond together and they form a new molecule. We can't do that because we don't have the powers in our chemistry labs and in what we're doing. So the only way we can do it is we have this Fe as a solo unit, and we can put 2 of those, right? You can put, let's say, 1 drop, 2 drop, or like 1 gram, 2 gram, right? But we can't take them and try to meld them together because that takes a lot of energy, and we don't have the resources for that. So that's why we can only do this, and we can't do that, okay? So whenever you're balancing equations, make sure to only put them in these blanks, as we see. Or if there's no blanks, put them in front of the molecule, all right? All right, let's keep going. Let me change my color. So what I see here is I see 3 SO4s, which is perfect because that's balanced over here. I see 2 FEs, which is perfect. And let's take a look at this guy. We have BR3, right? So we already have 3 BRs. We multiply by 2. What do we get? We get 6. So let's go over here. So we have our 6 BRs. So let's just say, let's put a 6 here, right? See if that works. So that means we have 6 H's, right? 6 H's, 6 BRs. So if we go over here to this H2 and the H2SO4, we have 2 H's multiplied by 3, right? We take those and multiply them together, and we get what? We get 6. So look at that, it works out perfectly. So if I erase this stuff down here, let's do our final check. We change colors for that. And let's see, let's start with our Fe. I see as well a Br. I see an H. So we have our Fe and our Br here. We have our H here. And then what I'm going to do is I'm going to put the SO4 as 1 unit, right? Because we talked about how that's just 1 unit. So let's put our dashes. And remember, the left side corresponds to reactants and the right side corresponds to products. So, there we go. So we have how many Fe's here? We have 2 times 1, which gives us 2. How many BRs? We have 3 times 2, which gives us 6. How many H's? We have 2 times 3 gives us 6. And how many SO4s as 1 unit? We have 3 times this 1, because we only have 1. That gives us 3, right? And then Fe's over here, we have 2 times that 1 coefficient, which gives us 2. BRs, we come over here and take a look. We have 6 times just 1, that gives us 6. H's, we also have 6 because we have the 6 coefficient, and we have nothing as a little subscript there. So we have 6. And SO4 is as a unit. We have a 1 here. We multiply that by this 3 here. So we get 3. And would you look at that? All the numbers are exactly equal. The 2's are equal, the 6's, the 6's, and the 3's. So our final answer would be 2 FeBr3 plus 3 H2SO4 will yield, we like to say yield, 1 Fe2SO4 plus 6, oh that was a really bad 6. There we go, plus 6 HBr. All right, let me clear this board and let's do another one. Let's do our last one. All right. So by now, I'm sure you've kind of recognized the pattern. You want to find, what I like to do is I like to find the solo one on either side of the reaction. In the last example, let me go back. The last example, oops, can let me go back? There we go. Last example, we didn't actually have a solo, right? We had 2 on the reactants and 2 on the products. So that didn't really work. But in letter D, in this example, we do have a solo. So that's right here, right? We only have 1 product, whereas we have 2 reactants. So let's try the products, okay? Start with that. Let me erase this so we have space. So what I see here, let's start with the carbons actually. I see 2 carbons, and over here, I see 4 carbons. And the thing is, these are the only carbons in the entire reaction, right? We only have 2 versus 4. So what are we going to do? We have to multiply this by 2, right? We got to put a 2 coefficient there, which ends up giving us 4 carbons and 4 carbons. So that checks out, right? The carbons are the same, perfect. But remember, this 2 gets multiplied across to here, to there, to the hydrogens, and all the way to the oxygen. So what does that mean for us? That means that we have this 2 here, and then, or this 4, right? We have 2 times 2, which gives you 4. And then we have this 4 times 2, which gives you 8. And then we have this 2 times 2, which also gives you 4. So in the end, we have 4 carbons, 8 hydrogens, and 4 oxygens, right? So let's take a look at this guy right here, this big guy. So we have our 4 carbons, which is perfect, which equals our products. But we have 6 hydrogens and 3 oxygens, right? And that doesn't really equal. So if we have our 8, if we take the 8 hydrogens on this side, minus 6, right? Minus the 6 hydrogens that we have right here. What does that give us? That leaves us with 2 hydrogens left over, right? And then if we have these 4 oxygens on the products, minus the 3 that I see right here, what does that leave us? Just 1, right? We need 1 oxygen left. And don't mistake that for a 10, that's 1 oxygen. And if we take a look right here, it's our lucky day, right? We have 2 hydrogens and 1 oxygen, which is exactly what we need. So we can actually just put a 1 here and a 1 here, and I think we'll be good to go. Let's double check. So I see carbons, I see hydrogens, and I see oxygens, right? So let's put our little dashes right here, and right here. So remember, this is for the reactant side or the left side, and this is for the product side or the right side, right? So let's see what we got. I see 4 times 1, right, times that 1, is equal to 4. I see 6 times 1 plus this 2 over here. So 6 plus 2 is equal to 8. And 3 times 1 plus this one right here is equal to 4. Ooh, let me erase that 8. Let's do that again. That wasn't so good. There we go. And then on the product side, or on the right side, we have 2 times 2 is equal to 4. We have 4 times 2, which is equal to 8. And then we have 2 times 2, which is equal to 4. Would you look at that? They're the exact same on all sides, which means that our equation is balanced. Technically, you could just not write these ones. We could, let me erase them and show you. You could just leave them blank because that implies that we have a 1. But if you like to be fully sure, you can put a 1 there and a 1 there so that nobody can mistake and see and accidentally read it wrong, right? So we have 1 molecule of C4H6O3 plus, oops, we have a plus right here, plus 1 molecule of, I think you know this one, H2O, which is water, which will yield 2 molecules, right? Because we have this 2 molecules of C2H4O2. Awesome. So let me clear the board and we can talk about some cool things. So we had a 1 here and a 1 here and a 2 here. So this is actually something called a ratio. This can give you a ratio, right? And it can, in higher math, it can, or not higher math, higher chemistry, a little bit later after you master balancing equations, you can use this to kind of convert between how much of this you have and how much of this you have. So let's say we put in 2 grams of C4H6O3. You can use this conversion factor to figure out how many grams of C2H4O2 you'll get out. We can put an X there or a question mark because we don't know quite yet. Oh, let me fix that. There we go. Because we don't know quite yet what we're going to get, but we can use that and we can do this chemistry, we can do some of this math to figure that out. So that's a really, really good application to balancing equations. All right, I hope this helped. And my name again is Vanita. Yeah, take care.